Hey everyone, welcome once more to our YouTube channel. So today we are going to be looking at a problem in the KC National STEM exam, particularly the physics entry for the advanced level. It's a question on parallax, an amazing concept that astronomers use in order to estimate the distances of distant cosmic objects from us. And we had to teach the students what parallax is right there in the exam and then go ahead to set problems that will require them to use their cognitive abilities in tandem with what they have been able to understand regarding parallax to solve real life problems across the universe. Let's dive right in. So right here, we took our time to really describe what parallax is to the students. So this is our opportunity to teach them in the exam what parallax is. So they had to read this, and then I'm even trying to demonstrate, explain how you can demonstrate parallax with your hands. You can just go ahead and pause the video and then check it out, and we dive into the problem. So the first question says, if the distance between the left and right eyes of Francisca, a 2023 STEM candidate in Boya, is 6.4 centimeters, how far must her finger be from her eyes for her to observe a parallax of 0.0011 degrees? By the way, Francisca is one of our students at the center here. It's a massive pleasure for us to be able to teach such an amazing girl. And yeah, spending our weekends teaching them advanced level physics. It's a joy, really. So this is your finger, this is two eyes. So if you close this eye, your line of sight will be here. So your finger will appear to be somewhere here. Now, if you now close this eye, your line of sight, this other eye would see your finger to appear somewhere here. So the angle between these two parallel positions, these apparent positions really, and your finger is what we call the parallax angle. Okay, so this is the parallax angle. So all of this angle like that is a parallax angle. The astronomers really what they refer to as parallax is really just half of the parallax angle. So this is our parallax angle right here. So we can go ahead and say that theta would be y over x, right? We're just using basic algebra. It's a concept I've just taught them in an exam. And then they just have to go ahead and then use basic algebra to be able to solve them, analyze problems on the concept. So if we make x a subject, we're going to have x as y over tan theta. In this case, x is basically the distance of your finger from your eyes, right? Good. So what is our x? Our x is y. What is our y? Remember that your y there is a distance from her eye, maybe two. It's really half the distance between her eyes, really. So you have 3.2 centimeters there, which is that in meters, and then tan of the angle between them. So we have theta there, but the parallax angle is 0.0011 degrees. So the parallax here would be half of that parallax angle, right? Because that's what we define parallax to be. So you have that, and so that answer is 3334 meters. And so our answer there is C right there. So the next problem says astronomers find the concept of parallax to be instrumental in measuring astronomical distances in the universe. However, since the changes in stellar positions are quite small, astronomers use really small units, the arc second, to measure parallax. Given that in a complete circle with 360 degrees, each degree is made of 60 arc minutes, and each arc minute is made of 60 arc seconds, how many arc seconds are in 2.78 times 10 to the power negative 4 degrees. Okay, this is really just counting, right? So again, it's an alien concept that we're showing students. So we just wanted to test how comfortable are you with doing the basic good things that you're able to do in normal countings, like how many 100s are in 1,000, how many ones are in 100, right? How many tens are in a million? That's really what is happening here. So we just really wanted to see how the students can respond in handling alien concepts with basic stuff that they are quite familiar with. So we're going to, of course, go there and say 360 degrees means that in every 360 degrees we have 360 degrees, and of course we can convert those 360 degrees to what? To arc minutes. So there are 60 arc minutes in every degree. Did you see that? In each degree is made of 60 arc minutes, and each arc minute is made of 60 arc seconds. So you are converting the degrees now to arc minutes, and then you multiply by 60 to convert to arc seconds. So you have in every 360 degrees, you have 1,296,000 arc seconds. So you can go ahead now and then say, all right, so if 360 degrees gives you this number of arc seconds, so these degrees will give you how many arc seconds? Well, you can just multiply this by this number and then you divide it by 360, right? So you basically have 1 arc second. So you can write an arc second as double prime prime like that. And arc minute, you can just have one and then a single, like inverted comma really. So if they are double, that's arc second. Okay. So that's really what you had to do. So the answer there was just E. And then our next problem is, okay, below is a diagram representing the effect of parallax on an observed star, Proxima Centauri, between two positions on the Earth's orbit about the Sun, P and Q. Given that the orbital diameter of the Earth about the Sun is 300 million kilometers, and that alpha is 1.52 arc seconds, how far in light years is Proxima Centauri from us? Okay, this is now a real life application of the concept of parallax, right? So we can just go ahead and say, okay, so you have 1.52 arc seconds as the angle here. We have to convert that to degrees. So if we're converting that to degrees, remember that at each arc second is 2.78 times 10 to the negative 4 degrees, like we've just proven. So if we multiply that, we would have this arc second will be equivalent to 4.22 times 10 to the negative 4 degrees. So we've gotten this angle 8 degrees. Now we can go ahead and say, all right, tan alpha on 2, because again, the parallax is what? Half of this angle between the two apparent positions. So tan alpha on 2 is R over D. And this is alpha on 2 here. What's our R? Our R is a radius because all of this is the diameter, so we now have from the center all the way, that's the radius, divided by the distance from the sun all the way to, again, where the Proxima Centauri is. So that's D. So we can go ahead and make D the subject because we want to find out how far it is. So it's R over tan of, well, we're already taking alpha over 2 because this is our alpha. If you divide that by 2, you have this. And so our D is basically, remember that our diameter was 300 million kilometers. So the radius there would be half of that, which is 150 million kilometers. So in meters, you would have that. So if you divide, then you have D as 8.14 times 10 to the power 16. But remember that you want that in light years, right? So 1 light year is 9.5 times 10 to the power 15 meters. So you have to ratio this by that. So divide this by 9.5 times 10 to the power 15. And then you would have 4.3 light years approximately. And that's our D. So our answer there is D. What must be the diameter of the dime if the diameter has a parallax of 1 arc second, 3.54 kilometers away? Okay, again, we just really have to understand parallax really well. So again, solve this. This is a daily live application of the concept of parallax, right? So we have this dime and this is the radius. So we have the entire diameter, but this is the radius. I'm interested in the radius because again, remember that I want to use basic algebra to find how far away this dime must be to observe that parallax. So we're just going to go ahead. So tan of theta over 2 would now be what? Because all of this angle is theta, so we have tan of theta over 2, so that we just define this angle. So it's opposite over adjacent, so we have r over x. And so we can go ahead and find r, which is now what? So we're looking for the diameter. Okay, let's look for the radius first. So the radius now will be x tan theta over 2, right? So remember that our x is 3.54 times 10 to the power 3 because that's 3.54 kilometers. And then tan, our parallax there is 1 arc second. 1 arc second, remember that it's 2.78 times 10 to the negative 4. When you divide that by 2, because you have to divide that by 2, right? You would have 1.29 times 10 to the negative 4 degrees. So when you multiply these two out, you have 8.59 times 10 to the negative 3 meters. But remember that you're looking for the diameter of the dime, right? So that diameter now would be 2r, which gives you 17.2 millimeters. And that's actually right around the mark of the diameter of the American dime. Thank you guys so much for watching. I hope you enjoyed it. And I think that again, you really enjoyed looking at how to learn a new concept and then just be able to use your basic understanding of basic classroom concepts to be able to solve real life problems around that concept. Again, this is what we do in the STEM, and if you liked it, please share the video to your friends, like, subscribe, and turn on the notification bell. See you next time.